Hello everyone, welcome to 1.5 Degrees, the podcast where together we explore the science, solutions, and stories involved in the fight against climate change. I'm your host, Heidi Pan, speaking with the professionals behind the latest research, policies, culture, and innovations shaping our response to global environmental challenges. For today's episode, we are joined by Dr. Matthew Rodell, who is the Deputy Director of Earth Sciences for Hydrosphere, Biosphere, and Geophysics at NASA's Goddard Space Flight Center, where he leads 400 scientists and engineers within 5 labs involved in remote sensing and numerical modeling of land and ocean processes. Dr. Rodell is also a member of the science team for NASA's Gravity Recovery and Climate Experiment Follow-On, or GRACE Follow-On mission. He also leads the Global Land Data Assimilation System and other projects focused on monitoring groundwater storage changes, mapping, forecasting drought and wetness, and detecting climate-related variations in the water cycle. Also the current editor of the Journal of Hydrometeorology, an awarded and highly cited researcher with more than 140 peer-reviewed publications. Dr. Rodell, thank you so much for being here.
Yeah, thanks for having me.
Before we go into discussing your research, could you tell me a little bit more about what it is that you do on a day-to-day basis?
Yeah, so I've been working for NASA since 2000. I started working there right after my PhD. And basically, a lot of people don't realize that NASA has an earth science department. It's actually a really large part of NASA's mission is to study the home planet. So we use satellite observations because it's NASA. We launch satellites, they go up into orbit around the Earth, and they make various types of measurements that we use for understanding the planet. I'm a hydrologist, so I use satellite observations that are related to water resources, the global water cycle, droughts, floods, that sort of thing. And on a day-to-day basis, it's not as glamorous as it sounds. I mean, I spend a lot of time in front of my computer, like a lot of people. Sometimes I'm analyzing data. More recently, I've taken on a more administrative role. So I actually lead an organization within NASA of about 400 total employees who are focused on various parts of earth science, using satellite observations, models, et cetera, to better understand our world and the impacts of climate change, and that sort of thing. So yeah, but I still try to do the science when I can. The science is the part that really excites me. And again, I'm a hydrologist, so that's my main area. And in particular, I've been involved with a couple of missions, the GRACE mission and the GRACE Follow-On mission. GRACE is the Gravity Recovery and Climate Experiment, which I think we'll get into soon. So maybe I won't step too far ahead right now.
Oh no, yeah. I mean, we could totally talk about what GRACE Follow-On is right now and what it's like for you and your team to work with these systems.
Yeah, so when we talk about remote sensing of Earth, you can think of a satellite orbiting the Earth, and most satellites are sort of looking down and either making measurements in the visible spectrum. We can think about things like Landsat and some of the higher resolution observations that go into Google Maps and Google Earth, that sort of thing. Or they might make measurements somewhere in the other parts of the electromagnetic spectrum. So different wavelengths of microwave are good for different things, like measuring the amount of snow on the ground or the amount of moisture in the soil, the amount of the greenness of the plant canopy, that sort of thing. But what makes GRACE and GRACE Follow-On different and really special and unique is that instead of looking downward, what these satellite systems do is they're actually, so let me go back a little bit. GRACE launched in 2002, and it lasted until 2017, and then we launched the GRACE Follow-On pair of satellites in 2018, and they're still currently in orbit. So both missions, GRACE and GRACE Follow-On, had 2 satellites. They're basically orbiting the Earth in tandem, so one following the other, about 200 kilometers, 130 miles apart. And instead of looking downward, the key measurement is the distance between the 2 satellites. So again, 130 miles apart, and they're measuring this distance every 5 seconds with a precision down to the size of a red blood cell.
Oh,
so
wow.
It's an incredibly precise measurement. The reason they're doing that is because it's a way of tracking the orbits of the satellites and how those orbits are being perturbed by mass or gravitational variations on the Earth. So, as you may recall from physics, the gravitational potential of gravity is related to the amount of mass of two objects. And so where there's more mass, there's more gravitational potential. And so you can think of the Earth as bumpy, right? I mean, there are mountain ranges, and then you got like the ocean goes down to the Marianas Trench. And so the mass is not evenly distributed around the surface of the Earth. And therefore the gravity of the Earth is not homogeneous. So if you went, to the top of Mount Everest, you wouldn't notice it, but you would be slightly heavier up there, a little more mass. Not enough that you would notice, but to a satellite that's orbiting the Earth, basically, almost in a vacuum, those gravitational changes are enough to influence the orbits of the satellites in a predictable way. So going back to the measurement, as we make these extremely precise measurements of the distance between the satellites, and then combine that with precise location information, over the course of a month, you can put together all those observations within a regression routine in a supercomputer and come up with a new map of the Earth's gravity field every month. So we now have these, based on the Grace follow-on data, we have these maps, month-to-month maps of the gravity field, and therefore how the gravity field has changed. Why does the gravity field change? Because it is not completely static. So it has the static component, which is like the mountains and that sort of thing. But there's also changes in mass, on the Earth. So you can think things like ocean circulation and tides. That's a big movement of mass. Atmospheric circulation is the same thing. When atmospheric pressure changes, that means there's more mass of atmosphere above you. And then on the land, variations in the amount of water stored on and in the land surface is actually a huge amount of mass. So if you had a big snowstorm and that it had a couple inches of snow on the ground, you add up all that snow over a very large area, and it's incredibly heavy. It's a very large amount of mass. And again, that's enough. It might not seem like much, but that's enough mass to affect the orbits of the satellites. So with these month-to-month changes in the gravity field, we can then basically strip off the atmospheric and oceanic contributions to the observed gravitational and therefore mass changes, and what's left is the mass changes associated with the terrestrial water cycle. So Grace tells us basically month to month, how is all the water stored on and in the land surface, which we call terrestrial water storage, how is that changing? Terrestrial water storage is basically the sum of all the groundwater, the water that's stored deep down in aquifers, all the water in the soil below your feet, the surface water bodies, lakes and rivers, and any snow and ice. So if you add that up into one quantity, and if you thought of it like the water in your bathtub sort of going up and down as you either drain water out or put water in, that's what Grace is telling us, basically how that total water storage is changing from month to month. It cannot tell us the total amount of water, so don't ask me how much water is left in the High Plains aquifer or something like that.
Gotcha.
It can only tell us the relative changes over time, but this is still an incredibly useful measurement, because there's many places around the world where we just don't have good ground-based measurements or any ground-based measurements at all of these important water storage quantities. So let me stop there and let you ask your next question.
Oh, no, yeah. No, thank you so much for that. I really learned a lot just from that one question. My gosh. Yeah, so you mentioned, so your most recent paper, actually, that I came across on social media, I'll get into that. It uses observations from Grace Follow-On and notes how there are now more frequent, severe, and longer droughts or periods of rainfall and extreme events. I'm very much oversimplifying that, so I'll let you speak more on the implications of those findings. What exactly does that mean for us?
Yeah, so let me go back a little bit. You did a good job of summarizing that. Basically, what we did was we took the 20 years of data that we have, going back to 2002 from Grace and Grace Follow-On, and we developed an automated algorithm, a computer to basically identify where there were extreme events happening. So it looked for areas where this terrestrial water storage was significantly above or significantly below the long-term mean. And so obviously if the water storage is above the long-term mean, you might have flooding. We call this a pluvial. It's sort of the opposite of a drought. If you have like a lot of more rain than normal, or more rain and snow than normal over an extended period, then you're going to have waterlogged soils, and the aquifers are going to be relatively full. You may have some snow in the ground, full lakes and rivers, that sort of thing. Not necessarily flooding, but your water storage is near capacity, the land surface. Yeah, the other side of that is drought. Obviously everyone knows what a drought is, but you lose a lot of water. Aquifers can be depleted, that sort of thing. So use the GRACE data, identify floods, or pluvials, what we call them, in droughts around the world. It also tells us not just there's a drought happening here, but it tells us the entire area and how that area evolves over time in terms of, for example, the drought changes over time. GRACE data tell us how deep is the drought, or how much extra water is there on Earth, and then also obviously we know how long it lasts. So putting those things together, the severity, the spatial extent, and the duration, we come up with a metric called intensity. So we can basically give one number at each drought event or wet event that's happened in the past 20 years, based on its intensity, and then we can rank the intensity. And so one thing we found is the biggest event overall over the past 20 years, this huge and possibly still ongoing pluvial in Central Africa, where there's just a huge amount of excess water there. And that one's actually, it dwarfs all the other ones. It's much bigger than all the other events by a factor of 3. But the other thing we looked at was how these events been changing over time in the past 20 years around the world. And I think the most important, significant finding from our study was that there have been more of the really major extreme water cycle events since 2015. And maybe we're 2015 to present, these now 8 years are were the warmest in the modern temperature record, right? So the global warming is happening, 2015 to 2022, all those years are in the top 10 warmest years in the modern record for the world. During that same period, there were 4 major wet or dry events per year during that period, versus the previous 13 years, there were only 3 per year. So that's a pretty substantial increase. I can't say for sure that that's going to continue, but what we did do was, to do a little more careful analysis of this, was to do a correlation study between the monthly global temperature mean, or temperature, average temperature of the world, versus the monthly total intensity of all the ongoing wet and dry events around the world, based on the GRACE and GRACE follow-on data. And we found a strong and significant correlation between those two. And but we wanted to make sure, maybe something else is driving that. Things like El Nino. You always think about El Nino as a big impact on weather, locally and around the world. So we did similar correlation analyses with the El Nino Southern Oscillation, an index representing that, and then some other oscillations, or things like North Atlantic Oscillation and Pacific Datal Oscillation, et cetera. I mean, so we did some similar analyses with all of those, and those were somewhat correlated. They definitely have an influence. El Nino obviously has an influence, but none of them were as strong of an influence as the global mean temperature. So that gives us some confidence that as the world's warming, we are having more frequent and more intense extreme wet and dry events around the world. So we can use this as a predictor. If the world continues to warm, you can expect more and more intense events, these events happening. So I think that's the most valuable part of our study. What did I not explain well?
Oh no, I mean, oh my gosh, yeah, so I really like how you explained how you came to the conclusion. I mean, it's really important to also take into account other factors, and this is really such a complicated situation. So I mean, yeah, no, you explained it really well. I did have a question about, so you actually what is it that you hope in terms of like how this research would be utilized, like be it like public or public policy? So I guess like in preface of this question, I came across your paper on social media, like I said before, and there were a lot of people in the comments that were very skeptical, and some were like outright denying climate change as a phenomenon. So I'm very curious, obviously, as to what your thoughts are as someone working in research on skeptics and addressing the rise of misinformation as well. Um,
Yeah, I don't read those comments because I don't want my head to explode. I mean,
yeah,
some people you will never reach, or they're just trying to get a rise out of people,
that's
and
true.
they
Yeah.
want to get some attention or whatever, and so I just don't bother with it. But
Mm,
I think among the reasonable part of the population, it's pretty well understood that climate change is happening, and it's caused by a rise in greenhouse gases that we created. So I'm not going to belabor that point. But I think what's important is that when you think about global warming or global change, I mean, people think, okay, well, the temperature's increased by 1 degree over the past however long it is. Like, if I raise the thermostat 1 degree in my house, I don't really feel that much. Like, it doesn't seem like that big of a deal. But really, it's the impacts of the increased warming, things like impacts on the water cycle.
mm,
They're the things we're going to feel. That's what's tangible, right? So when the ice sheets are melting in Greenland, in Antarctica, and that causes sea level rise, and there's flooding along the coastline. That's something that affects people, a lot more than an increase in temperature by 1 degree. And
mm,
similarly, floods and droughts. I mean, when you have a major drought, and it impacts agriculture being grown, and it raises prices at the supermarket, or have trouble, you got to water your lawn, whatever it is, that has an impact. Obviously, flooding can have really major impact. There are huge economic losses in the U.S. caused by droughts and floods each year, and around the world it has you know you, not only the economic impacts, but also can cause regional unrest, and actual migration of people, and obviously hardship and death and that sort of thing. So we want people to be aware that this is one of the consequences of climate change. It's really going to affect people. So this is the rise of, or the increase in frequency and intensity of wet and dry events is something that people have predicted. It's something that's come out of climate models,
mhm.
and people have made other predictions, but it's been very difficult to sort of prove with real data. And so this is one of the first times that we have real hard data that show
Yeah.
that it's really happening. I mean, it's not just someone's theory anymore. I mean, we can point to the data and say this is real.
Mhm.
And so to me, that's what's really important, is and perhaps that'll drive partly drive policy. Maybe people become more serious about using uh, more efficient appliances, going towards hybrid or electric vehicles, installing solar panels, that sort of thing. Things that'll
Yeah.
eventually make the change, and hopefully turn things around so we can reverse the warming, and try to protect our home planet.
Yeah, our home planet. Yeah, no, I mean, first off, like what you mentioned about like not wanting to deal with those people in the comments, it really is like something that bothers me. But it is pretty smart to, not let that weigh on the research that you do and just like the work that you do in general. Um, I guess also like to speak more on like public policy, um, I actually want to bring in like a current event that like so the Willow project that was recently approved by this administration, it was like prior to its approval really criticized by a lot of scientists and researchers, and even like it continues to be criticized. So As in regard to this like kind of gap, I guess you could say, that's between researchers and public policy, what experiences have you had with bridging that gap?
Yeah, so as a NASA scientist, I have to be careful. My area is not policy. So, I
Mm,
always say that uh, that I provide the data and the analysis to help people understand, what's happening, with the climate and with the water cycle in particular. But it's up to others, policy experts to determine, how to interpret those data and develop policy based on that. So now what I'm about to say, I am not representing NASA when I say this. This is my own, sort of
mhm,
personal opinion. Clearly, in order to, you know, reduce climate change, it means reducing the amount of greenhouse gases that we're producing. With respect to the Willow project, it would be better if it hadn't been approved from a climate change standpoint. At the same time, my personal opinion is that
mm,
there's supply and demand that drive the use of fossil fuels, right? So
mhm,
this is on the supply side, but it doesn't affect the demand side. And I really feel like demand is what drives it. And the only way to
that's
reduce
true.
demand is to go to renewable sources of energy, higher efficiency appliances, electric and hybrid vehicles and that sort of thing. And that's how people can really have an effect. And if we do that, if we really start to ramp up our production of renewable energy, there'll be less need for the fossil fuels,
Mm,
and then it won't matter as much that it's available from one more place. And if the Willow project had not been approved, we still would have gotten our oil probably from Saudi Arabia or somewhere else,
that's
right? I
true.
mean,
Yeah.
it's hard to say that that's people have been trying to say, like, now our world's going to warm this much more because of Willow. Well, that's only if we actually use that fossil fuel, the oil that's pumped out of there. If we commit to moving to different sources of energy and that sort of thing, then it won't be as much of an issue. So that's my, again, personal perspective. And there's also the wildlife factor and that sort of thing. Like
Yeah,
that part
yeah.
bothers me a lot, right? I
Mm,
mean, beautiful pristine place, and then we're going to be putting
yeah,
roads through
yeah.
there, all the collateral damage from that's a problem too, obviously.
Mm, yeah. I appreciate that answer. I do realize, yeah, you are not necessarily like that involved in like the public policy aspect, but I appreciate your answer. Yeah. Um, okay, I mean, to go on to actually, I'm gonna turn back time a little bit, butterfly effects aside. Um, was there so you've been working in this field for some time now. Was there ever a moment that you kind of realized this is something that you wanted to do with the rest of your life? Yeah, and how did you kind of um what was like your journey up until this moment, I guess you could say?
Yeah. So I'm someone who believes in not trying to sort of steer the ship too hard, right? Like, I'm not someone it wasn't like I was in middle school and I said I'm going to be a hydrologist when I grow up and work for NASA. Like, there's never an epiphany like that at all. It was
True,
just,
yeah.
I've always been, loved being outside. I've always been a naturalist and concerned about the environment, our planet, and that sort of thing. And when I was in
Mhm.
college, I was in my beginning of my junior year, and I didn't know what my major was going to be. I come to college thinking I was going to be pre-med and that I was going to major in math, and then I realized
Mm,
I didn't like where math was going with, like, theoretical math and that sort of thing, and I wasn't very good at chemistry, so I kind of kind of fell out of the pre-med track, and I was sort of like, what am I going to do? And I was looking around the different options, and I realized that environmental science was actually a very new
mhm,
option at that time, and it was perfect for me. Um, so I became an environmental science major. I had a professor, um, Pat Burkhart, who is a really, like, a mentor to me, and just a fantastic teacher, and someone who really cared deeply about the planet, and I learned a lot from him. And he actually taught my first hydrology class, excuse me,
mm,
and so sort of got me into hydrology. And then at the end of my senior year, I didn't have a job lined up, and I was helping him move out of his house. He said, "Hey, Matt, what are you going to do next year?" and I said, I'm not sure. I'm kind of applying to jobs right now. And so, well, here's a card of someone I used to work for. Why don't you give them a call? And that ended up being, leading to my first job at an environmental consulting firm in New Jersey. Later on that year, after I'd worked for a while, and when you work, let me make a quick plug for gap years. When you take a gap between high school and college, or college and grad school, and you work in the real world, like you come back appreciating going to class. Homework sucks. All the doing all the work for school is hard, but the real world is harder in some ways, and so you definitely come back with appreciation. So after taking that year and working for a year, I went to graduate school at the University of Texas in the geology department. And I was reinvigorated in terms of taking classes, and I ended up meeting my PhD supervisor, who happened to have funding to support me to do a PhD. And so I said, great, I'd love to have funding to pay for my time in graduate school. And he steered me towards remote sensing hydrology, something I hadn't really thought about before, because I thought I was going to do like groundwater contamination hydrology, which is what I had done in my job. And so, it was an opportunity, and I took it. And I did really well with it. And the GRACE mission was actually developed originally at the University of Texas. So I was able to get in on the ground floor before it even launched. And my PhD research was a pre-launch study of GRACE and what it could do for hydrology, which is kind of a risk because no one even knew if, would the mission be a success. It was completely new, and blow up and launch or something, right? My whole PhD would be out the window. But everything worked out, and I ended up being one of the first hydrologists, involved with the GRACE mission, and that really set me up for the rest of my career. Helped me get my job at NASA and that sort of thing. So just to summarize what I've said, I mean, I had the things that I love, and I definitely wanted to work in an area that was related to my love, which was outdoors and environmental science and that sort of thing. But I took the opportunities as they came to me, and made the best of them. I mean, that's the other really important part of it, is you could, even if it's not your ideal, you want to make yourself indispensable so that you can use as a stepping stone to the next position, or get references from the people you work for and that sort of thing. And yeah, so I just took the doors that were open, made the best of opportunities, and worked really hard. And that's how I've gotten where I am. Again, not like an epiphany, not like me saying, this is what I'm going to do at all costs, right? I mean, it was more like I'm going to follow the opportunities.
Yeah, no, that's really, well, thank you for sharing that firstly. My gosh, yeah, like these kind of career paths are definitely a lot more organic than people often make them out to be. And so also, by the way, like chemistry is also not my strong suit. But yeah, no, I'm also personally very interested in environmental science. And you also gave like a very valuable piece of advice of taking on opportunities when they come, and also just being able to like, so you lead a team of 400 engineers and scientists. What would you say, kind of going along the line of like advice, what would you say is an important lesson that you've kind of learned from your experience as a leader specifically, and how did you come to learn that?
Well, I don't know. I have probably a lot of things I could say. One thing is, I always think of this, leadership and management positions, at least in NASA, as a service. So I didn't start out saying like, I'm gonna move up the ranks and be the manager and all that stuff. It was like I was happy being a scientist, but I was a scientist in a lab of about 60 people, and the current lab chief was moving on, and they needed a new lab chief. And I looked around, and it was like, if I don't do it, who's going to do it, right? I mean, so I stepped up, and I was selected as the lab chief, and that was my intro to becoming a part of management. And the same thing sort of happened with the next position up. I was a lab chief for 7 years, and then the position above that, which oversees 5 labs, the current position I have, that there was an opening at the associate level, so not the leader, but one, the sort of associate, sort of like vice leader type thing. And I applied for that. I just thought it was time for someone else to have a chance to be the lab chief, and for me to do something different,
Mm-hmm.
and again, sort of doing a service for the organization. And so I stepped up and did that. And next thing I knew, the actual the deputy director of Earth Sciences, who was my boss, she moved on within a year when I moved into that position. And then next thing you know, I was moving up, and next thing you know, I'm leading an organization of 400 people.
Yeah.
So yeah, I view it as sort of a service, and it was like, these opportunities were there, and I knew I would do a good job with it. And so that's sort of how I got there. And my leadership style is very much sort of hands off. I mean, I want people to be independent and to grow, and I want to, I provide them guidance and advice,
Mhm.
but I'm not up there like directing, like, you do that, you do that.
Yeah,
This just
yeah.
happened to be, that's the type of organization I'm in, is a scientific organization. Each scientist, more or less, is developing their own research ideas or contributing to an existing
Mhm.
project. So it's not like my leadership is more like government bureaucracy and,
I got you. Yeah,
and
yeah.
some sort of larger scale strategy, and not so much like giving people orders every day and that sort of thing.
Yeah, no, that's important too. I mean, leadership can come in all different types of forms. Can you speak more on like what you mean by so strategy management is that what you yeah.
Well, so the way that NASA distributes its work and funding is all competitive, meaning that if you want to do scientific research, even if you worked for NASA and you're a government employee, you have to write a proposal saying, this is the research I want to do, and
Mhm.
this is how I'm going to do it, and why it's going to succeed, and that sort of thing. And it's going to compete with other proposals from other NASA scientists and university scientists and private organizations and that
Mhm.
sort of thing. So there's this competition, and so we have to have some strategy in terms of how we're going to win these awards to do our science. So that's sort of the smaller level, but then the larger level is doing missions. So leading new satellite missions. Before you get to satellite mission, there might be a suborbital mission, meaning like a sensor on an airplane, that sort of thing, or on a
Mhm.
UAV. Um, so, and they're all different levels of missions. There are these smaller, we call them explorer missions, that or let's say, so they're small, but the number, you're going to think that doesn't sound small to me. They're like
Right.
30 million up to like 150 million dollar type missions.
Yeah.
And then you have the what we call the flagship missions, which
Mhm.
are bigger bigger missions that are really highly desired by the scientific community and by NASA. And those missions can be anywhere from $300 million up to $1 billion. Think of something like James Webb Space Telescope. I mean, that was multi billions of dollars
Mhm.
to build and launch that, because it was all new. No one had ever done it before, and there were all how many patents went into that, and new
Yeah.
technologies were developed, right? And so these are expensive things. So when going back to strategy, it's how are we going to come up with the new ideas and develop the people so that we have the teams to lead these ideas, and eventually capture these missions so that we have the work we want to do at our center. That's the big part of strategy.
I see what you mean. Yeah, no, it's such a complicated process and it's quite hard to fathom, but yeah, thank you for that. You mentioned earlier actually in our conversation that you like to try and get involved in science, in the direct science as much as you can. Is that what would you say that is like the best part of your job, or what is another like memorable project that you can think of that you were involved in?
So first, I get a lot of gratification from leading people and helping, mentoring people and that sort of thing.
Mhm.
So that's a part of my job I really enjoy too. But I do really get excited about doing the science, looking at the data and creating visuals and understanding it and coming up with new, writing papers, and
Mhm.
eventually some of the papers are the type that the general public can understand and are important, like the one we were just talking about.
Mhm.
Um, What was the other part of your question? I'm sorry.
Oh yeah, no. So in terms of oh gosh, I can't. Oh yeah, no. The part about like your most memorable project that you can think of.
Okay, so yeah, I mean, I've had a lot of studies that were really exciting. I mean, a lot of times when you're doing scientific research, um, some of the advances are incremental, and they're not things that the general public would care about, but they're important. It could be like
Mm,
improving a model or better understanding data or improving the algorithm that derives data from a satellite, raw satellite observation. These things are all important, but they wouldn't be newsworthy. So
mm,
the really exciting ones, a lot of times for scientists like me, are the ones that end up, they are newsworthy, and usually we do have an idea of like this one's going to be big. um, so the first one for me that was really big was back in we published back in 2008 a paper using the GRACE data where we noticed that over northern India there was a long-term decline in the terrestrial water storage. And when you map, when you take all the data and you basically fit a trend at each location on Earth, you can come up with a map of how terrestrial water storage is changing over
mhm,
time. And so, at that point, mission launched in 2002, so we only had when we started the study maybe 4 or 5 years of data, but we could already see that over northern India there was like this bullseye of water storage depletion, and it was like, whoa, what's causing that?
mm,
And it turns out that's an area where there's it's a heavily agricultural region. It's also semi-arid. Don't get a lot of
mhm,
rainfall. And so what they do is they pump huge amounts of water out of their aquifers and spread it over the land surface. Use it to irrigate crops. They grow a lot of rice, for example. For rice, you have to have rice paddies, so you're like flooding the surface with
mhm,
water,
yeah.
and a lot of that water either runs off or
Oh, I see.
evaporates. So as you're doing that, if you're constantly pumping water out of the aquifer or spreading on the surface, most of the water is evaporating. That aquifer doesn't have is not going to be able to recharge as fast as you're using the water, and that's what's happening in northern India. They're just dewatering their aquifers very quickly. It's a really dangerous situation.
Mm,
Dangerous in the sense that it's unsustainable. So at some
yeah.
point, you start to either the well goes dry and you have to dig a drill a deeper well, or you get down so deep that the water starts to become saline and not
Mm,
usable.
yeah.
Um, and this is obviously the population of India is huge, and they're depending on all this agriculture in northern India.
Yeah.
So it's pretty scary. I mean, they really need to find some more sustainable practices, which might be like growing less water intensive crops and putting
Mm,
some more restrictions on groundwater use to try to conserve the water that's there. Anyway, that was a big. So when we saw that in the GRACE data, we published a paper. How fast the water is declining in the aquifers in northern India, and it was, it got a huge amount of attention. We did, radio and TV interviews for it and all that sort of thing. So that was really fun. Um, and that was my first big one. So I guess I'll stop there.
oh yeah, no, thank you for that. Yeah, so oh my gosh, water is like so important to, like human life. Like it's basically the foundation of so many like human affairs. I mean, so you spoke kind of a bit about like anthropogenic like related projects that you've worked on. Um one of the questions that I have is like how do you determine the difference between something that's like natural climate event versus anthropogenic climate event?
Yeah, that's a great question. It's not easy, and basically what we have to do is make use of all the different data sources that we have. So one of the ones we look at is precipitation, first of all,
Mhm.
right? Like rain and snow, and we have good both satellite and ground-based observations of precipitation. Good, not perfect, but good enough that we can look and see, if there's for example, if Grace tells us that there's a trend of water depletion in one area, the first thing I'd look and see is like, is this happening because they've had less precipitation than normal, or
Mm,
perhaps it's something else? And if the precipitation data tell me that things should be relatively normal, then I would say, okay, well, it's probably something else. And then you would get into looking at things like irrigated agriculture, and we have maps of the intensity of irrigated agriculture around the world. So if, groundwater or water storage is being depleted in an area, it's an area where there's a lot of irrigated agriculture, and the rainfall's been fairly steady. I mean, that's a pretty good sign right there that water is being depleted because they're using the water to irrigate the land, and they're using the water in an unsustainable way. That's just an example, but it really does. And this is where it really becomes research, right? I mean, you have to,
Yeah.
Google's great. I can't even imagine what they did back, 30 years ago before we had the internet, trying to understand these things, and getting hard copies of papers and reading journal articles, and microfiche to look it up,
Right.
look
Yeah.
at newspaper and see what the events were in that region. So that type of thing as well, like news articles and other anecdotal evidence of what might be happening are important as well. But yeah, we really try to make use of all the different types of observations we have. Some of them, NASA satellite-based observations, some of them ground-based observations, and others, news reports and scientific literature and that sort of thing.
Yeah, no, thank you for that. Oh my gosh, yeah, I'm like personally also like kind of dipping my toes in the water of or unattended of what like research entails. And so I guess like to wrap up, what is like one last piece of advice you would give to someone who is like trying to get into what you're doing right now?
Um, I mean, that's a tough one. I would say, clearly you want to major in something, scientific area. I would look at, if specifically you're talking about NASA, I'd go to nasa.gov and look at all the different types of projects that are being done, what, remote sensing missions are there, and where are the areas that NASA's going. And then, if you can become an expert in one of that areas, obviously that's you're getting taking a step in the right direction. Most people who work at NASA as a scientist have been to graduate school. So, very few only have a master's degree. Almost all of them have a PhD first, or there are also others who have a master's degree. But if that's really your goal, you want to think about graduate school, and particularly working with a professor as your advisor, who's someone who works with remote sensing data. So if you're someone who finishes grad school, especially with a PhD, in one of these areas, hydrology, cryospheric science, biospheric science, and you've had experience making use of remote sensing data in your scientific research, then you've really got a leg up in terms of applying for positions. And obviously, if the better you are at doing things like programming, if you can write code. Believe it or not, a lot of our code is still in Fortran, but there are also people use C and Python and that sort of thing. And so if you've got that experience, and if you're good with manipulating large data sets, in a Unix or Linux environment, and you're good at visualizations, that sort of thing. Maybe use GIS, maybe use some other sort of tool for mapping data. Those are all things that are valuable skills to have in terms of when we're hiring.
Thank you for that. Yeah. Oh my gosh, GIS. Oh my God, I started using like Geoda, and like it's just so complicated to wrap my head around. But yeah, no, thank you so much, Dr. Rodell, for that. I certainly learned a lot from our conversation, and I'm sure listeners have as well. So yeah, thank you so much for being here today.
Yeah, thank you for having me. That was fun.